In this video, we continue our introduction to limits, but we're going to focus on when the limits do not exist here. So remember that we mentioned in the last video, in order for a two-sided limit to exist, that both one-sided limits need to exist and be the same. Okay, but what we want to know is when would they not exist? Because all the ones we've seen so far have existed. So there's three ways in which a limit may not exist. Now I'm talking about for two-sided limits. I'll mention briefly for one-sided limits what's going on. But just so we can, I wanted to split them in three because we kind of write them a little bit differently. Okay, so the first one is one that we have already sort of talked about. I'm going to draw a picture of what happens here. So imagine that we're approaching, say, A, okay, and maybe our graph as we approach A comes down to some y value, maybe let's call it L, and then on the other side it approaches some other value, okay, maybe something like this, and maybe this value is M. Okay, so because of this jump in the graph at A, we would say the limit doesn't exist. So let me write that a little bit more explicitly. So what's going on here is we have the limit as x approaches A from the left of f of x is going to be L. And the limit as we approach from the right is going to some number M. Okay, and L is not the same as M. Okay, so the right and left limits here are different, but they both exist, but they're different numbers. Then, okay, what we would write in this case is the two-sided limit as x goes to A of f of x does not exist. Okay, so we write DNE for that. Okay, so here's an example where it wouldn't exist because the left and right limits are different. Okay, so that's sort of one that we mentioned before. Okay, there's another one, there's two more where the limits approach actually a number that doesn't exist. Okay, so in this example, they both approached a number that did exist, but we could imagine that we had something like, maybe like an asymptote. So maybe here's A. Okay, A is not in the domain. But maybe the function approaches, so in this example, okay, they're both going to positive infinity. Okay, so what's going on here is f of x, so the limit as we go to A from the right of f of x is, or actually, sorry, I'm going to write this a different way. So as x approaches A from the left, okay, our y values, f of x, approach, let's say, positive infinity. And as x approaches A from the right, our functions also approach positive infinity. Okay, now it doesn't have to be positive infinity, I just wrote what matches the picture. Okay, so I'm just going to write same infinity on both sides. Okay, so they could both be approaching negative infinity. Okay, then what we would write, this limit still does not exist. Okay, so it's an example of when the limit does not exist. This limit, x goes to A of f of x, okay, does not exist. But here, we use some bad notation, okay, and we would write that the limit as the two-sided limit of f of x as x goes to A equals infinity, positive infinity in this case. Okay, or negative infinity, depending on, okay, so or negative infinity if that is the one they approach. Okay, so what I want to point out is that infinity is not a number, okay, but does not exist. Okay, so even though we can talk about it and we can write it and we can use it to do stuff, it seems like it's a number. It's not. Okay, it doesn't exist. We just use it to say that the things are getting really big, okay, or really small. They're going to negative infinity. So the idea here in this case is that they're approaching the same infinity, okay, on both sides. Okay, the idea with number 3 is that they maybe approach different infinities. Okay, so maybe we still have something like above, where we have an asymptote, and it could be that one of them approaches a number and one of them goes to infinity. That's still, they're different. Okay, in this case, let's say, I don't know, it goes like, maybe it approaches positive infinity on this side, negative infinity on this side. Okay, so here they're going to different infinities. Okay, so as x goes to a, I'm going to write what's in my picture here. So as I go to a from the left, f of x goes to positive infinity. And as x goes to a from the right, in my picture, f of x goes to negative infinity. That doesn't really look like a positive. Okay, so again, what I mean by this is they approach different infinities. I missed an I there. Okay, so here, the difference between the last one and this one is here they're approaching different infinities. Okay, so they're approaching different infinities. Then, because they're different, we again write the limit as x goes to a of f of x does not exist. Okay, so dne. So the reason why in number 2 we write it slightly differently is because they're going to the same place, we kind of want to be able to say that. Okay, so because they're both going to positive infinity, it's almost like they're the same. Okay, they're going the same place, okay, just that place doesn't exist. So that's why it's an example of a limit that doesn't exist. But we write it just saying which infinity they both go to. Okay, so on either side, you're going towards positive infinity. So on the next one, you'd have to talk about the left and right limits explicitly if you wanted to say which infinity it goes to, because they're going to different infinities. Okay, so that makes it different. So we're using dne. So imagine when they're not the same. Okay, so here they approach different numbers. Here they approach different infinities. That's when we write dne. If they approach the same infinity, whether it be positive or negative, okay, it still doesn't exist because infinity doesn't exist, but we're going to write equals whatever infinity they approach. Okay, so that's the idea. Let's do some examples. So the first one, we want the limit as x goes to 1 of x squared minus 2x plus 1, okay, all over x minus 1 cubed. So remember, let's try and plug in x equals 1, see what happens. Okay, so on the top, I get 1 squared minus 2 times 1 plus 1. And on the bottom, I get 1 minus 1 cubed. So it looks like I have 0 over 0 here. Okay, so that sort of tells me I need to do some more work. Okay, so let's think about the function inside. Okay, so can I rewrite this? Okay, so it turns out that we can factor the top, and it's actually a perfect square. So it factors as x minus 1 all squared. Okay, so now I can actually cancel, okay, 2 of these and with 2 of those on the bottom. Now this is only true if x is not equal to 1, because you can't cancel 0 over 0. Okay, but if it's, we want the limit as we go to 1, so we actually are never going to plug in 1, really. We want what's happening as x is close to 1. So we're allowed to simplify to 1 over x minus 1. Okay, so as long as x is not 1, the function we started with and this function are the same. Okay, they're going to give the exact same values. So when we're taking the limit as x goes to 1 of our initial function is actually equal to the limit as we go to 1 of our reduced function. Okay, and this is because, okay, so this is since we don't care what happens at x equals 1. Okay, only near x equals 1. Okay, so we're allowed to simplify inside the limit like this, which we're going to talk about in the next section. Now, I want to use a different color. Okay, if we plug in 1, because remember that we always want to try doing that when we're doing limits, we're going to get 1 over 1 minus 1, which is 1 over 0. Okay, now this is different than what we had initially when we had 0 over 0. Okay, 1 over 0 actually does tell us some information. So what happens when you divide a number, so like 1, divided by a number that's really small? So remember that this bottom is not actually 0. The bottom is just close to 0. Okay, so we're dividing by a number that's really close to 0. So if you take 1 and you divide by 0.0000001, something really close to 0, you're actually going to get a really big number. Okay, so this is going to go to plus or minus infinity. So right now I can tell you that this limit doesn't exist, but I want to know if it goes to, I want to know on either side if they approach the same infinity or different infinities. Because I want to know if we're in case 2 or case 3 in our examples for does not exist. Okay, so that's the idea. So what we're going to do is look at the left and right limits. Okay, so let's do the right one first. So if I go to 1 from the right, I'm going to use the simplified one because I'm allowed. Okay, so I want this limit. I'm just going to leave a spot for the answer here. So I'm going to write it, I'm going to do each of them in a different color. So let's use green for this one. Okay, so as x gets close to 1 from numbers that are bigger than 1, okay, x minus 1 we know is getting close to 0. But what I want to know is, are these numbers going to be positive or negative? Okay, so I'm plugging in something here that's slightly bigger than 1. Okay, so let's say 1.001. Okay, so if I subtract 1 from it, the 0 here is going to be something slightly bigger than 0. So what I'm going to do is write 0 plus. So I remember that this is slightly bigger than 0. Okay, so a positive number. Okay, so why I need that is now what I'm going to do when I do 1 divided by x minus 1, it's 1 divided by a really small positive number. So I have a positive number, the 1, divided by another positive number. So I'm going to end up with a positive number. So this tells me that this side is going to positive infinity. Okay, so I know that this is positive infinity now. So I'm going to write this as positive infinity. Okay, so this limit is going to positive infinity. Now I want to do the exact same thing from the left. So here, 1 minus 1 over x minus 1. Again, I'm going to leave a spot and switch colors. Maybe I'll use gray here. So now we're going to 1 from the left. So I'm slightly less than 1 now. Okay, so think about this. I'm plugging in a number here that's slightly less than 1, so 0.99999. Okay, I'm really close to 1, but slightly less. When I subtract 1, I'm subtracting a number that's bigger. So that means that I'm going to approach 0, okay, but this time I'm going to be negative. So I'm slightly smaller. Okay, so I'm using our plus and minus notation in another way. So I'm slightly smaller than 0. So now, when I do 1 over x minus 1, I'm taking the number 1 and dividing by a really small negative number. So I have a positive number divided by a negative number. This is going to give me a negative number. So this value is going to be going to negative infinity. So that means that this limit is negative infinity. Okay, now because the left and the right, sorry I did that in the opposite order, okay, the left and the right limits are going to different infinities, what I'm going to write is that our full limit, so our two-sided limit, I'll write our initial function, okay, does not exist. I didn't need those equals, but you can have them if you want. Okay, so because they're different, okay, so I have plus infinity, minus infinity on the other. Because they're different, that's why I get the DNE. Okay, that does not exist. We're in case 3, it turns out. Okay, let's try another one. So here I have the limit as x goes to 0, absolute value x over x. Okay, so if I plug in 0, I get absolute value 0 over 0. Okay, this is just 0 over 0. Okay, this is bad. So it means that I need to do some more work. Okay, now in order to do that work, what we're going to want to point out, okay, so you should, this is maybe something you haven't remembered, but you will have encountered this at some point. Okay, so if you want to work with an absolute value, you can actually use it as a piecewise function. Okay, so in the first piece, let x be positive. Okay, so or bigger, non-negative, bigger than 0. Then absolute value, the absolute value isn't going to do anything. So we're just going to get x, whatever x was, because it's positive. Okay, now if I'm less than 0, I'm going to get a negative number. So when I take the absolute value of it, it's going to make that number positive. Okay, now a way to write this, which sometimes confuses people, is to write negative x. Okay, now this is a positive number because I have a negative and then a negative number. Okay, remember double negative makes a positive. So we're going to use this to simplify our function. Okay, so if I have absolute value x over x, I can also do this in a piecewise function. Maybe I want to move over a bit. Okay, so if x, now the 0 is not in the domain, so I'm going to be strictly bigger than 0 because I can't divide by 0. So if x is positive, the absolute value is just x, the bottom is also just x, which means that this side's going to be 1. Okay, so if I'm bigger than 0, my y value is 1. Maybe I'll just write here. Okay, so exclude 0 since it's not in the domain of absolute value x over x. Okay, so we can do it when we're just talking about the absolute value, but when we're dividing by the x here, then we have to remove it. Okay, now if x is negative, the absolute value of x is going to be negative x, okay, over x. So here the x's cancel, and what I actually get is negative 1. So you can actually graph this. Okay, what it looks like is it's always 1 when you're bigger than 0, and it's always -1 when you're less than 0. And there's no point when x is 0. Okay, so this is the graph of absolute value x over x. Okay, now this will help us find the limit as we go to 0. Okay, maybe you can already tell what it is, but let's do the left and right hand limits, because 0 is, we've now written our function as a piecewise function, and 0 is where it splits. Okay, so if I do the left limit of absolute value x over x, then I know that this is actually, because I'm slightly less than 0, when I do this limit, I'm going to be in this category here. Okay, so I'm actually taking the limit of -1. Okay, now think about as we approach 0 from the left, okay, we're following this line, we're approaching the value -1. Okay, we're always -1, so actually we're not even approaching it, we are that value. Okay, so this one is going to be -1. When we're doing the right hand limit, okay, so now I'm slightly bigger than 0. Now I'm in this category, so I'm taking the limit of 1, which is going to be 1. Okay, now notice that these limits are different. So what that means is that our two-sided limit does not exist, because we got two different answers here. Okay, now I just want to talk about one more, but with a graph. Okay, so we have a bunch of different ones here, but we're reading from the graph. So here's a function, f of x. Okay, there's a whole bunch of points that are illustrated here. So first of all, I want the limit as x goes to 6. Okay, again, two-sided limit. So we want to think about when x is getting close to 6. So we're going to be approaching along the curve from both of these directions. Okay, but we're approaching this point, and this point has y value 2. Okay, so this limit is just equal to 2. It's a nice point. Whoops, I have a color here. So it's a nice point. So you're just approaching it. It's like you were able to plug in 6, you got a number 2. Okay, what about when x is getting close to 0? Okay, so I want the limit as x goes to 0 of f of x. So this one is a bit interesting because I have this point here at 2, so 0, 2, but as I'm getting close to 0, I'm actually approaching the y value 4. So does this point affect the limit? Keeping in mind that the limit only cares about what happens near the x value. Okay, so I don't care what happens at the x value, only near. And near, I'm going to be along these lines. Okay, so on both sides, okay, they're approaching the number 4. So this limit is going to equal 4. Okay, so you could also write the limit as we go from 0 from the left of f of x is 4, which is also the limit as we go from the right. Okay, and f of 0 equals 2 doesn't matter. Okay, because we want near the limit. Okay, the next one is at x equals 4. So here it looks like we're x equals 4. So it's similar to the last one, except now 4 is not in the domain, right? So there's no point when x is 4. This doesn't change anything because remember, we don't care what happens at 4. We only care to near 4. Okay, so near 4, we're going to be approaching the y value 1. So this limit is going to be 1. Okay, -4. So what happens as we get close to -4? Okay, so that's over here. So now we can see that we have a jump in the graph. Okay, anytime there's a jump, your limit's not going to exist. So y, if we approach from the left, we're approaching the y value 2, but if we approach from the right, we're approaching a different y value, 3. Okay, so what we're going to write is that this limit does not exist. Okay, and then I'll write the left and right limits. So as I approach -4 from the left, okay, we went to 2, but if we approach -4 from the right, we went to 3. Okay, so these are not the same. So that's why we get does not exist. Okay, now we want as you get close to -6. So let's go up to our graph again. -6 has a vertical asymptote. Now, if we think about from the left and from the right, from the left, we're going to positive infinity. From the right, we're going to negative infinity. So again, we're going to write dne. Okay, so since the limit, so you go to -6, from the left of f of x, okay, this I'm going to write equals, but it doesn't exist. Okay, but it's going to positive infinity. And the limit as we go to -6 from the right, again, I'm writing equals, but it doesn't exist, but it's going to negative infinity. Okay, so let's just write these both don't exist. Okay. And they're different. They're different infinities. Okay, so when you have different infinities, that's why we get dne here. Okay, last one, okay, x equals 3. So there we have another vertical asymptote, okay, but here from the left, we're going to negative infinity, and from the right, we're also going to negative infinity. So what we would write here is this one equals negative infinity. But what we want to remember is this still does not exist. Okay, we write negative infinity since both the limit as we approach 3 from the left approaches negative infinity, and the limit as x goes to 3 from the right also approaches negative infinity. Okay, so because they're the same infinity, that's why we're writing that this one is negative infinity. Okay, but remember, it still doesn't exist. Okay, so this is still a dne case. Okay, now notice here, I've sort of talked about the left and right limits. For the left and right limits, you're always going to write that they equal something. Okay, because the only way that they cannot exist is if they go to infinity. Okay, so they're either going to equal some number, or they're going to go off to plus or minus infinity. Okay, but you're always going to have equal something. But if they go to infinity, you have to remember that we write equals that infinity, but we really mean does not exist, because we have to remember all the time, infinity is not a